for canceling last week. I was very sick all week, so I didn't even have really a chance to make it up.
And the chill homework.
Yeah, it was relatively chill.
2 was interesting. I have not graded all of it yet, but I've graded a bit of it. So people did relatively well on 2B. People did exotic things on 2A. So I feel like I always see like held breaths when I say like some problem didn't go as well as like people were, because I'm like, was it me? No, so basically, if you remember 2A, it was showing that you could make a right linear grammar for any regular language, right? So the easiest thing to do by far was going from DFAs.
I think I.
So a lot of people went from regular expressions, which is harder.
I did not do that.
Yeah, that's quite a bit harder.
I think.
I mean, you can do it, and there's, I think, an elegant way to do it, but you have to be a bit more careful. DFA, the construction's not so bad if you go with the DFA model, because you basically just have to say, well, if I have some transition like let's see, from QA to, so Q0 is your start state, obviously, and then if you have some transition equals QJ, let's say, so QI goes to QJ, then you make some, let's call all our variables like AI, AJ for the grammar. Then you make the following rule. A, I, A. So what is it?
Looks like the camera's a little bit blurry.
Goes to, sorry. Camera's, oh yeah, the camera's super fucked up. Holy crap. Okay, why are you doing this? It's something about when I get closer to the camera, it tries
like
to
focus.
Tries to refocus. General video really doesn't like. Whoa. It's so messed up. Change what it's actually doing. It's just going to change whether it's doing. So let's see. Oh my god, it's so bad. Thanks for letting me know.
Yeah, for sure.
This is just horrible. Oh, it's audio. I'm so stupid. Yeah, it didn't work. I have no idea where that setting is. Let's, can I turn it off and on somehow? What if I remove the device?
And then re-add it.
Yeah. I'm removing it mid-recording, which is weird. I think it's okay though. I don't think the OBS cares. It's never been that bad. That's much better. I just don't know how to get it to stay that way. Okay, I won't get near the camera.
Okay, don't get near the camera.
I don't know, I just have to be extra careful, I guess. Okay, so Q0 is our start state. And basically you just make a rule for every, so if you have this, you make this rule.
Yeah, I think I did something.
Does that make
like
sense? Yeah. And then if QI is the final state, then you add epsilon.
Yeah, I did. I think I did.
That's it. Yeah. But a lot of people, it was just more like they got off on the wrong foot, and it's hard to recover because they were like, let's do regular expressions. But then if you do regular expressions, you have to go through all the basic rules of regular expressions and come up for a way to turn those into right linear grammar rules, and it's not pretty. But if you see this, then it's okay. All right. So that was last week. What about this week?
Personally, I am like having a real hard time. I don't really understand like push down automata like at all.
Sure.
I don't know how you feel. Okay.
Okay.
I'm just so lost, and I just like.
Sure.
Yeah.
Think about it maybe like this. I mean, if you guys are you guys both programmers?
Yeah. Or I am.
Yeah. If you guys both know how to program, then you may have dealt with situations where you're going to be dealing with like an array, for example, and there's rules for like adding elements to arrays and sometimes you want to like take elements out of arrays.
Mm-hmm.
Imagine that basically you have a DFA, or not a DFA. What is this like?
An epsilon anything.
Yeah, something like that, and it doesn't really matter. You can have a DFAs are equivalent.
That's true.
But basically, it's like you have that plus you have an array, but you can only add things to the start of the array and take things out of the start of the array. So that's why it's called like that's what the stack is really, right? Because when you're adding new things to the stack, another way to visualize it is to think of it as like some list, like 1, 2, 4, and now at every step I can like ignore the list essentially, or I could take the first thing out of the list and use the fact that it's a 1 to influence my decision, or I could record something into the list. So like maybe add a 3, but it has to go at the start.
Mm-hmm.
Right, so like if I add to the list, and if I take out of the list, then it ends up this. So that's what the stack is.
Mm-hmm.
But the important thing is that one of the big weaknesses of things like DFAs was this whole issue with counting, right? But the stack gives you some limited form of counting. It's not perfect. It's definitely not up to the standards of a Turing machine.
Mm-hmm.
But if you look at the language that was used on the previous, so for 2B, the most commonly used non-regular language for the example was this language. For I greater than or equal to 0. Right? This is a non-regular language. But a PDA can definitely accept this. Why?
Because you can keep track of like or
yeah, how would I do that?
A stack.
So imagine so basically all you have to do is you make a DFA that in addition to when it looks at an A, it adds an A to the stack. Or it adds a dot to the stack. It doesn't matter. It's just trying to count the number of A's it's seen, right? So it adds A's to the stack every time and then goes back to the same state. You really only need here's a way to visualize it sort of like a DFA. I don't know how he's sort of tried to give intuition for it in class, but I think he's probably given some stuff like this. So you've got this state, which if it sees B, it goes over to here. And what's his syntax for removing from the stack?
So A, comma, B, that's the B's being it's going to be top of the stack, and then slash C, C's being the thing that's pushed
into the stack. Okay, so it's going to be like B slash A is what's popped from the stack.
Yeah.
And then he puts what you push on the stack, which I'm going to make epsilon.
And except there's like a slash.
Instead of a comma.
Yeah.
Oh, okay. Where's the slash? It's
the second comma is
got it.
So A, comma,
yep,
B
makes sense.
slash.
So we're going to have this B, comma. Do C usually use parens?
No parentheses.
Okay. So B, and we're going to have A slash epsilon. Does that look like what he does?
Yeah.
Okay.
So what does that mean? So you're reading a B from the tape, and then you're popping an A off?
Yes.
And putting so you're not putting anything.
And you're not adding anything back.
Are you allowed to do both? Are you
yes.
allowed to put? Okay.
I mean, it depends on the formalization. I actually haven't read his specific definition. You don't need to add that rule though, because you could just send to a state that's all that state does, right? You can basically there's ways around these. So people define these things in slightly different ways that actually have no effect. In the sense of if you don't allow someone to pop and push at the same time, you could have it pop and then go to a state that adds something new and then goes back to where you wanted to end up.
Oh, okay.
This is cleaner
Yeah.
to be able to pop something and add something in the same step, because then you don't need weird states that really all their job is to add something to the stack. You still need those sometimes, but I prefer this definition, and it sounds like this is what he's using. So we go with that. Here it's a read A. Oops, that's not an A. Read A. Pop nothing, add A.
I think that step, I think he said is not allowed. Like the way he kind of defined it, he said it would only pop like the Z naught, the start of the stack, the bottom of the stack. I think he said we cannot pop epsilon from the stack if I remember correctly.
Sure. Let me
Like
look
where
at his
he's-
formalization then,
sure.
really quick. Sorry, I probably should have done that before, but
The bottom of stacks.
see, I want to
Yeah.
use the syntax
So
he uses, but
push down and down. That's the way like he's doing it. Usually he's like popping like Z naught instead of epsilon.
I see. So Z naught is what?
Is like the bottom of the stack. It's like it's not epsilon. It just like it's a special symbol saying that it's the bottom.
Oh, you know what he's doing? The thing he's doing here, I think, is so Z naught is the bottom of the stack. Fine. This is what you're seeing on the stack. It doesn't necessarily mean you're popping it. So I see how he's formalizing it. It's a good way to formalize it, honestly. So here is what you see on the tape. Then this first symbol is what you see on the stack. This is what you replace it with on the stack, though. So if I want to add an A to the stack, it's sort of like, I'm going to have two rules here. A sees Z naught and adds an A to the stack. Okay? Or A sees A and replaces A with AA. Does that make more sense?
So wait, when you say like sees it, does that mean it's like if that's on the top of the stack, then you do that?
Yes, then you replace the top of the stack A with
those.
AA, which is
Oh.
essentially you adding an A to the stack, right?
Okay, so here you see the first one. I think he also like puts Z naught back in it. He just treats it as just a symbol, but it's always there, always at the bottom.
So if he sees A with a Z naught, right, okay. So if he sees A with Z naught, then he wants you to make sure to be careful, and the bottom of the stack is to the right, correct? Yeah. So the bottom, like my array, where you could only look at the first symbol, the stack, the bottom is over here. So Z naught A.
Oh, you're putting Z naught back on.
Yeah, you always need that at the bottom of the stack.
Oh, okay, that kind of makes sense.
Yeah. So basically, if you want to write onto the stack, it's always overwriting the thing you read. Essentially,
Always
right?
popping something.
So if you do epsilon, it's popping it and putting nothing back.
Wait, can you say that one? Like,
So basically, when I read this, it's kind of ripping it up.
oh,
so
if you
some-
read an A, so you have to put two A's
So you have to
back
put, that's
on.
why I'm putting two A's back.
Oh.
There's just a couple different ways to define PDAs that are totally identical.
Okay.
Which is one, it's like you read it and you don't necessarily rip it up, and so now you have to decide, do you want to get rid of it or do you want to add something onto it? But they're all equivalent.
Okay.
And in this course, when you read something, you're essentially getting rid of it, so you need to replace it. And you need to add anything else you want to add to the stack then as well. Does that make sense?
Yes.
Great.
Okay.
But you see how a lot of these different formalizations could be equivalent? It's just like changes how you would make the instructions slightly,
Yeah.
but they're basically the same thing.
Okay.
Between DFAs and PDAs, there's something fundamentally different, right? Like you have added power.
Right.
With some like minor modifications to definitions to these machines, though, they're just like the same. You
Okay.
just have to change how you think about them a little bit.
Right. Yeah.
So this sort of thing is something you can't do with a DFA, right? Is that here what I'm doing is every time I see an A, I'm putting an A on the stack so I can count it. For a DFA to count, you basically need to make a new state for every one you wanted to be able to count. But notice here that I don't know how many A's I'm going to read ahead of time. So if my DFA has 1,000 states, then if I get 1,001 A's, it's not going to be able to count anymore, right? but the stack is not bounded in how much information you can add to it, right? It does have some restrictions, but yeah.
So like, I'm kind of thinking about like question 2, but like if whenever we have like a bounded stack, it means it's a DFA.
Exactly.
Yeah.
And so like, the bounded stack thing is basically like, just think of your states as containing information about the stack, right? And we've sort of done this sort of thing before, right? Where we'll have a state that sort of indicates you've seen, let's say you accept the language of every binary string that doesn't have 3 ones in a row,
Mhm.
okay? Then really all your states are indicating is one of them is the state where you have seen no ones in a row. Another state is where you've seen 1 in a row, 2 ones in a row, and then there's a trap state for if you've seen 3 ones in a row, right? But if you ever see a 0, before you see 3 ones in a row, you reset, right? So the states are kind of keeping track of something finite. If your stack is limited to something finite, though, then you can sort of keep track of your stack by using states to do that. And you can also think about another example, which is sometimes you know how you'll have a question where you need to sort of combine the functionality of multiple DFAs. So let's say you have a DFA that accepts a string with, I don't know, it's some number of repetitions of like, it's like the machine that accepts this. Let's see, it uses plus here, I think. So this is regular, right? And then I could have another language that rejects anything with 2 ones in a row. So basically, all strings, all W, uses W a lot. All W such that W has no consecutive ones. So that's also regular, right? These are 2 regular languages. So one way to combine their functionality, okay, this one is rather easy. It's either going to be all of these or all of these, because if you had, if you ever did this one and then this one, there'd be 2 ones next to each other. So it would not be in the language. So if I wanted the intersection of these 2 languages, for example. I see confusion. So these 2 are regular, right?
Yeah.
Right. This one, you just do the trick we just talked about, where you count the number of ones you've seen in a row. For this one, you just have like 2 branches. One where if you see a 0, you try the branch where it's 0, 0, 1, and if it ever violates that, you go to a trap state. If you see a 1 first, you go through 3 states to check it's 1, 0, 0, and then you just loop back to the start each time, or go to a trap state if you mess up. So both of these are definitely regular. We know the intersection should also be regular, right? One way to quickly design a machine, though, for this, for the intersection of these 2 languages, is to make a machine where every state essentially encodes the information of the states you're in for both of these, and you only accept if you're in a final state for both of these machines. Does that make sense?
Mm-hmm.
So basically, the state I want to start in here was Q0 and here was Q prime 0, let's call it. So I might do some formalization like Q0, Q0, right? And then my transition function is going to be, sorry, Q prime 0. My transition function is going to be, if it takes in Qi, Qj prime, and then, I don't know, A, then it spits out delta, that's a terrible delta of, let's see, oh, not delta, of course, it's going to be, yeah, no, it is delta, oops, okay, so it's going to be delta of Qi A, it's going to, j. Okay. Right? Does this make sense?
Oh, so you like start in like you have like a tuple of like states from machine 1 and machine 2, and then
Yes.
like you like read a symbol, and then you just kind of like go to wherever it would go in the first machine,
Right.
and where it would go in the second
So
machine.
how many states does this have? If this has let's say k n states and this has m states, how many states does this machine have?
I feel like k plus m is too simple.
It's so if this is m and this is n, or let's say sorry, I used
I don't
I
remember
and
the letters.
j. It's fine. K, we'll go with yours. K and m.
K and m.
Then it'd be k times m, right? Because it's all pairs.
Oh, you're totally right. You're totally right.
Yeah, and it's ordered. It's ordered pairs,
Yeah,
right?
yeah, yeah,
Because like being in Q0, Q prime 2 is not the same as being in Q2, Q prime 0. But this makes sense, right? So, and it's still finite. That's the important part. Is yes, you have to increase the number of states, but it's still finite. So this is what you should kind of be trying to pick up on with respects to the PDA, right? Is that your original your PDA would have had some state, and its stack would have had some state. But the states of the PDA, like the number of variables in the grammar is finite, and the number of stack configurations is also finite. And so when you multiply these together, you should still have finite configurations. The reason a stack is ever interesting is because it's unbounded in its size and its configurations, which is not something a DFA has access to. It has no way to like deal with something like that.
So are you saying like for each state, there's like in your PDA, like there's a different stack configuration that could be like associated?
Essentially, yeah.
Okay.
You could be in that state with this stack configuration or with this stack configuration.
Oh, okay. That's kind of making a little bit more sense. Okay. Let me look at the question from the homework. And then there's this thing with like the I don't know what the symbol is called, but it's kind of like a T that's like on the side.
Yeah, one sec.
Let me see if I can like figure out what that thing is actually called, so I can like be like more legit.
I'm just gonna look at something.
I don't know what this is called, and I don't really understand. There's like too many things going on, and I just like can't really parse it. I don't know what this is. I don't really know how to like.
So we define the relations from the configuration.
I don't know what that thing is called.
So all it's saying is that this relation exists if when reading one symbol, this symbol A, one of the states you go to is Q prime with stack configuration beta.
So like you can reach that state.
And the reason that there's this other symbol there, I can't remember what symbol it is, the like R looking thing.
Oh, is that gamma? Or
don't
no,
know.
I don't know.
Does anyone
It might
speak
be.
ancient Greek?
It looks like one of those gamma rays. Or
I think
whatever.
if it crosses, it's a gamma,
Oh.
right?
I'm calling it. It might be rho, but I'm not
No,
sure.
rho is like that,
You're
unless
right,
it's
it is.
capitalized.
Okay, it's gamma until someone tells me otherwise.
Okay, bet.
And
'Cause
so,
this is
so basically, what it's saying though is it's saying that regardless of what's happening deeper in the stack,
yeah.
X becomes B. So, so I put this.
Is this for one?
This is a
general-
definition.
yeah.
This is a general definitional question. We're talking about definition 16.4,
Okay.
which builds off of definition 16.3. So you kind of have to look at them together.
Okay.
But basically, 16.3 tells you how to describe where you're at, sort of like it's the current state, what you haven't read yet, and what's on the stack. So this is the configuration of the PDA.
Right.
So the 16.4 definition is essentially the definition of what it means for you to be able to get from Q to Q prime in a single step. So basically it's saying that can you read multiple things off the top of the stack at once?
No.
No.
Okay. It's interesting that he uses X then. Oh, I guess that makes sense. So basically X is going to be some symbol on the top of the stack that's influencing your decision, influencing your transition. And you're going to replace X with some beta. But that doesn't affect anything deeper in the stack, right?
So is this the thing that's on the stack that we haven't read yet?
So Q is the state you're in.
Yeah.
AW is the string you're reading. So it's like in
Okay.
the DFA where you read left to right the string and try to end up in an accept state. See where you end up. Does that make sense? So like if I have an input to a DFA, it might be 0, 1, 0, 1. So in this case, I would break this up as W and A. So this is the next thing you would read to influence your decision of where you go in the DFA, right?
Oh, wait, but I thought don't you read? No, you read left or right.
You read left to right.
So when you have read the A first.
That's why it's separate. Yeah, you'll read the A first.
Oh, okay.
Yep. So basically, you'll notice that you have, what was it? So in the first one you have AW, and the next one you have W, because you've already read that A now, and you're not going to consider it any longer, right? So like if I go from one state to another, there's one less symbol for me to consider from the input.
Oh, okay, yeah.
Does that make sense?
Yes.
Okay. So you're going from Q to Q prime
Mm-hmm.
because you saw A,
And then you read it, and
and then the stack had X on top.
Yeah.
And now you're going to state Q prime. The A is no longer there, just the remainder of the string W. And the whatever X was on top of the stack will now have been replaced with something between epsilon and some arbitrary string of stack alphabet elements, right? Because you'll replace X kind of like how I replaced this A with two A's. So this would be X in this example,
Yeah.
and these two A's would be beta, would be the capital beta. They're what you're putting on the stack when you go to Q prime. So this is sort of like a single transition in like an NFA or something, right? So this relation is all it's saying is this relation holds if when you are in this state with this first character in this top of the stack,
Right.
you can end up in Q prime without A and with beta on top of your stack.
Okay.
It's saying that this relation is true essentially if the PDA is defined to do that.
Okay.
The
Gotcha.
relation is false otherwise.
Okay.
So if you have this relation, then notice it's if this relation holds if and only if Q prime beta is in the transition, right? It's if Q prime beta is one of the things you would go to from Q A X, right?
Oh, okay.
So the relation is true if and only if this is one of the states with the stack new stack top that you would go to from starting from Q A X. Does that make sense, everyone? Cool. It's fine if it doesn't. I just can always answer more questions on it.
Yeah, I think personally, like, there's just so many like different like characters and like symbols, and I just keep getting confused
Yeah.
and like overwhelmed.
It's very easy to get overwhelmed by
Yeah.
notation before you have intuition for the object it's describing.
Yeah.
Yeah. You really like. Personally, I have never found it easy to parse lots of symbols jammed together, and I think it's really just. I guess I think of it. I think of a lot of these representations as a sort of arbitrary way of representing something I have some intuition about, right?
Right.
So it's
But I just don't have it.
Right. No, I mean that's the whole idea of the course, right? Is to
Okay.
gain an understanding of these concepts, and I think that if you're having trouble remembering or like parsing a pack of symbols, then that's normal because until you understand what those symbols are there for and what each of them are doing, it's kind of just arbitrary memorization.
Yeah.
If that makes sense.
That's not really helpful with like math.
It's
then
quite
you-
difficult
yeah.
if you do it that way, in my opinion. I don't have the best memory, so I'm sure some people can brute force it this way. I cannot.
Yeah.
So.
Same.
I don't quite understand how just in like it comes up in like 16.4. But I guess from 16.1, how for the transition in the here in the transition function, how you can have multiple things.
Because this is important because his formalization of PDAs
Mm-hmm.
requires that you essentially anything you read off the stack is essentially gone after you read it. So
Yeah.
right, so if I see this is a half-drawn example. Sorry, but if you see an A on top of your stack,
Yeah.
well, that A is gone by our way of formalizing things, right? There's always something here, but reading it destroys it.
Yeah.
Right? There's always a single stack symbol, but reading it destroys it. Well, if we could only replace it with a single character, then our stack would not be very useful because our stack could literally only ever have one symbol on it at that point, right? Because you would remove whatever you're reading, and then you would add back something. And this is actually then, because the stack alphabet is finite, that would mean the stack would have a finite set of configurations that would actually reduce it to the power of a DFA.
Yeah.
Right?
Which is like problem 2.
Exactly. But here, if you need to be able to place at least 2 characters, right? Because otherwise your stack can't grow.
Yeah.
This definition allows you to place any number at once, which is also fine. Because what if a time that would be convenient, actually, let's do a cute example of why this formalization might be convenient, is, let's actually keep this as I. What I want to say is that this. How can I adjust my machine easily to now accept this language instead? So, and here I have, what is it? It's reading B, popping A, and this is, if it reads, what do we do for, what's the right thing?
For the same number of eyes and
What does he allow for if you read the, I just want to see how he formalizes. Q is a finite set of Okay, so you can read epsilon. That's all I cared about. Or is epsilon transition right? So is it? Yes. So I can take a state. I can take an epsilon, and I can ask for something from the type alphabet. So I can do this, right? Epsilon Z0 to a final state. That has no other transitions, right? And it doesn't really matter what you do here. Put Z0 back, I guess. So then if your stack is empty.
Oh, you just put. Oh yeah, because you put the bottom stack symbol back on.
Yeah.
Okay.
And I think you'll have to do the same transition from over here too, right? Because if it's you have the empty string, then my definition allows for it. And in fact, that's kind of annoying, and I want to erase this line, so I'm just going to make this 1. Just make my life easier. Does that make sense? Okay, but I changed the language. It doesn't work anymore. So this is what the machine would have looked like for, and notice that if I didn't write a transition, basically it just goes to a trap. You can imagine it going to a trap state, or just that line of computation disappearing, but it's just so much easier to draw DFAs when you allow yourself to not draw lines for the things you're not looking for. With limited board space. Okay, so how could she was asking basically, why does the definition allow for you to see X on the stack, but replace it with like Y1, Y2, etc., etc.? Why is it useful to be able to place so many things? So we already knew why it's useful to place 2 things at once, right?
Yeah, because you need to replace what was already on there.
Exactly.
And
But
add
let's.
a new thing.
But here's an example of a time where it's convenient, not necessarily more powerful, but convenient to have your definition allow you to place multiple things on the stack.
Wait, you can do more than one extra thing on?
I think so.
Oh.
Is that what the definition allows? It allows up to K.
Oh, that's what it's saying.
I believe so.
Okay.
I've seen tons of different formalizations of PDAs, so it's always a little bit different each time. It's usually very small differences. Yeah, I see no reason. It's bounded up to K. I don't know if K is presumably finite, but we can set it ahead of time, I think.
Okay, cool.
Oh, actually, yeah, K is going to be finite. You do have to pick some finite set of characters to put onto your stack, but
Yeah.
so why is it helpful now that we can put more than 2 things on the stack?
So we can keep track of the A's and the B's.
So
Not quite.
if you put at the beginning, every time you read an A,
Mhm.
you put, it's like A instead of,
Exactly.
because then you get twice as many B's as A's.
Done. Because now think about it. Every time you read a B, you remove an A, right? And so for the stack to be empty and for you to accept, now every time I read an A, I remove 1 A and add 3 A's, right? So every time I read an A, I essentially add 2 A's to the stack, right?
But I thought you want more B's than A's.
You do. But you are counting, essentially what you're doing every time you remove a B is, remember, you can only read 1 character off the stack. So the
Right.
B's are only removing 1 A at a time. So for the number of B's, so what happens every time you read an A? How many more A's does the stack have?
2.
Right, okay. So now, whenever I read a B, how many A's do I remove from the stack?
1.
Right. So how many B's would I have to read to remove all of the A's from the stack?
Oh, twice as many.
Exactly.
Oh, okay.
Does that make sense?
Dang, I would never come up with that.
So these are just like these examples are really just to help you think more flexibly about PDAs and see how they can be useful. And also this example is to illustrate, one of, I think, the hardest things for people and for us graders actually is when people come up with exceptionally complicated answers to questions that have some like elegant answer. And so like trying to play with these machines and come up with like elegant ways because a lot of the questions on the homework, right, they're variations on things you've seen in class.
Yeah.
So a lot of times you can kind of take something from class or from the lecture notes, and you just need to know how to make simple adjustments to it so that it meets the criteria asked for in the question, if that makes sense. And so it's useful to sometimes think about this sort of thing. And like the thing we talked about of tupling DFAs, right, where you have, these sorts of tricks can be very helpful.
Can I ask a question from the PSET or?
Yeah. Definitely.
For 3, oh, that's kind of funny. I know, we have to do pumping lemma.
Yep.
But I get confused about all the cases that we have to break it up into.
Right. That sort of depends on what string you decide to pick. But do you people understand why this pumping lemma works? Because like
Not really.
now you guys have an understanding of the original pumping level,
Yeah.
right? And why that would make why if you can pump something, it's not going to be regular, like, and how basically the finite states make sure there will be a loop somewhere, right?
Yeah,
And
'cause
so
if the word is longer than the number of states, like it has
Yes.
to like.
it has to have a loop
Absolutely.
somewhere, and you take advantage of that loop to show that, in fact, no matter where in this string the loop happens, the machine is going to get confused and accept some things it shouldn't accept or not accept enough.
Yeah.
So this is sort of similar, except now we have a stack, so we actually can keep track of. You may never, you can have infinitely many different configurations of the machine, right? Because even though you only have finitely many variables, and the string you're reading is finite, things like that. Like finitely many variables in a grammar, or the string you're reading is finite. The number of like different stack configurations you can have as the size of the input increases is unbounded. So you can't take advantage of that same sort of trick. I personally find it's most revealing to think of why the pumping lemma works with respect to grammars. Why this new pumping lemma works with respect to grammars. Alright, which is to say that, what's the form it has? You mind if I erase all this? We good on this?
Yeah, we're good.
So grammars are definitely a lot more complicated. But the thing about the grammar is that eventually, what letters does he use when he breaks it up into 5 pieces?
What?
Oh, like the tuple.
Oh, U
Yeah,
V X Y Z.
Okay. So this is going to have length less than or equal to n or something? Alright.
Yeah, or
Greater
U.
than or equal to N.
Oh yeah, that whole. Oh. Yeah.
The whole thing.
The whole
has
thing
to
is
have
greater than equal than it.
Yeah.
Yeah.
So the whole thing is greater than or equal to n. I thought some substring has less.
Substring.
Yeah.
Yeah.
VXY is less than n.
VXY, that's what I thought, yeah.
Yeah.
VXY is less than n, and these,
And then
one
V.
of these is not empty.
Yeah.
Let's do less than or equal to n.
So can you strategically make one empty?
So the important thing, you can make one empty, but usually it's sometimes a case you have to consider more than anything else. So what's the important thing to note here, though?
VXY, that's less than.
Yeah, VXY is less than n.
Yes.
Not UVX.
So the reason for this
Oh.
is that now we're not worried about the number of states, right? We're just talking about a grammar right now. Okay, so states aren't even really in the equation. What we're going to talk about, the reason we care about this like n is it's not indicating states, it's indicating number of variables, right? So think about the variables you have in your grammar. If you start generating a string based on some, production rules from your variables, your first variable is s, right? It's your whatever your start variable is. That might lead to some other variable a, right? A might lead to some some symbols with with some new variable a included, and a might lead to some new symbols with some new variable b included. The important thing is there's a finite number of variables, right? Because you have a finite number of grammar rules, and each of these are going to have some subset of the variables associated with them. But basically, at the end of the day, your generation rule either makes no variables or some subset of a finite number of variables. Does that make sense?
Yeah.
Right? Because your grammar might have S, A, and B, and those are the only variables. N is getting at that. Because what we will basically want to say is that after you've seen this much occur, you have a repeat of a variable you saw earlier.
Oh yeah. Okay.
Does that make sense?
Mm-hmm.
And that variable can generate all the same things it could before. It doesn't, like, if I'm making some string starting from S and then I go to A and then I go to all these other variables and then something generates another A.
Mm-hmm.
The string I've already created could get created again.
Yeah.
By the A.
Because you're reading the same.
Because you're reading the same variable, and that variable has no memory as to how many times it's existed within the string, right? So that's essentially what you're pumping against, is you are trying to show that, like, you take something in the language and show that because something about it's going to force you to have the same variable multiple times, you can have this problem where that variable can generate something outside the language if you pump it.
Yeah.
Trying to think of a...
If it's not in, wait, what are we saying? That if it's not context free, then
Then it shouldn't have a context-free grammar
Yeah.
that generates it, right? That
Yeah.
generates exactly the strings in the
you
language,
would
right?
arrive at something where the variable produces something that is in the language.
So you take something in the language,
Okay.
before you, okay, for the original pumping lemma, you
Yeah.
took something in the language, but you took something in the language strategically. You took something in the language that was large enough that you could be assured that it would have a loop somewhere, that it would enter the same state twice, that the machine reading it would enter the same state twice in doing so at some point. So you know there's a loop. Here what we're doing is we're going to pick something in the language that had the same variable appear twice in its generation.
Yeah.
Does that make sense?
Mm-hmm.
Yeah.
Now,
the same
yeah.
variable. Okay.
And you don't know exactly where that variable showed up, but you
Right.
do know it's appeared, that some variable has appeared more than once in the generation of the string.
Right.
Mm-hmm.
And because of that, you can now pump that variable, essentially, like the string that variable creates, and say that, okay, well, this string is in the language, but actually the variable can generate, inevitably, can generate things that are actually outside the language, and so this isn't context-free. Because the A, like, let's say you had an A occur twice, the A would have needed context to realize it shouldn't generate the same substring again, but it doesn't. That's why we would say it's context-free really comes from the fact that the variables pay no attention to what's around them when they generate new things, right? All of the rules only include variables. They never include, like, a single variable. They never include multiple variables. They never include, like, symbols. Because, like, what if I could have a grammar rule that was, like, something like this? A, B, C generates something. This would be context sensitive. Because it cares about what's around it. And it's paying attention.
Oh.
Sorry, I don't know if you ever explained, like, where context-free comes from. I find it helpful.
Yeah.
It's context-free because the variables have no idea what's going on around them.
Yeah.
And that's what this pumping lemma is taking advantage of.
This is so cool.
Does that make sense?
I love the pumping lemma. Like, I love it for, like, regular languages.
Yeah, yeah,
It's
yeah.
my favorite thing.
Yeah.
The pumping lemma
It's fun.
is horrible when you don't understand
That's
it, and
true,
really
yeah.
cool once you do.
Yeah.
And so now that hopefully gives you a better idea of why this all these shenanigans are happening. Why don't we? I think I only have a few minutes left before I gotta go. But yeah, I got like 9 minutes. So why don't we talk a little bit about? We could talk a little bit about the homework problem one.
Yeah, I personally, I don't know about
I don't like to go
y'all.
too deep into homework problems to
Right.
spoil the fun, but
Yeah.
we can handle. What do people think is a good way to pump this? So, of course, once again, we have to start with something. We have to start with something that we think will be able to, like, pump in an interesting way, and you'll want to take advantage of similar things to the original pumping lemma. It's just a bit different in the sense of, like, there was a time where basically, like, for original pumping lemma, think about sort of like, let's go back to AI BI, because this question is really the successor of this is
Right.
question 3 on your current homework is really just the context-free version of showing this language is not regular.
But you don't have to have A, B, C be the same number to the same power. No.
So remember that this language is not regular, right?
Yeah.
What I'm saying is this is definitely context-free.
Yeah.
Right? So what he's doing is he's making the language a little more complicated, and now it's not context-free. So this is essentially that's what I mean in that this proof in question 3 that you're going to need to do is very similar to showing that this is not regular. So showing that is not context-free is quite similar to showing that this is not regular.
Okay.
So what was the way we kind of, if our pumping length is n, what would we choose our string to be?
I think it was like something like you split up the AI into two things that like add up to I. Sorry.
A.
You make the word
Yeah.
A N B N.
Exactly.
Okay.
And so I know I taught a different pumping
Okay.
lemma,
Yeah.
but I'm going to go back to sort of his type of pumping lemma now because it's more similar to what he's given you for context-free languages, and I don't want to give you a whole new one for context-free.
Yeah.
So A N B N is where to go, right? Why is this such a good choice?
Because it's automatically greater than n because it's like 2n.
Right,
Yeah.
exactly. And we know, because we know there's a loop after, n states.
Yeah.
We know there's a loop in that's only A's. Right? Does that make sense? We've made the first part long enough. It's not just that the whole string is over length n. Certainly that's necessary. But we've done something better. We've made this length n, which means that, so if you're in the machine, right? Every time you take a transition, you go to a state. If there's n states, and you start in the first state, there's only n minus 1 other states to go to. So after you've read n characters, you must have been in the same state twice. So the difference between the pumping lemma I presented you guys a while ago and his pumping lemma is basically the reason his is shorter is because he's assuming the loop, he's only paying attention to like kind of like the first time the loop happens.
Oh.
His loop always happens at the beginning of the string. For me, I kind of let you choose where the loop happens. So the way I defined it. But for this context-free definition, that's why this is less than or equal to n. Because he's forcing you to have your first like occurrence here in the first part of the string you're reading. So here, what I've done is I've made sure that the loop only contains A's. So why does this make the pumping lemma proof super easy?
Because there has to be a loop somewhere in the A's.
Yeah, and which has somewhere between 1 and n A's, right? Because the loop can't be empty, right? So somewhere you now have something of the sort like A, I, I don't like this. Let's see. I don't like using I here.
Could we do like A, S, like T? I usually do S and T. And they
I'm
add
gonna
up
use
to
like I'm gonna start from C, I think, and
Okay.
just use those as constants. So if I have like a C, and this is a D, and this is I can't do F, G, or H.
You could do L.
Yeah, I'll do M. Whatever. I skipped a lot of letters. Okay, so if you have something like this though, and let's say this is the part getting pumped, but that C plus D plus M
equals n.
equals n, exactly, right? But then if I pump this, well, I can either remove an A, in which case there's now clearly less A's, or I can just add as many A's as I want, but it's always A's.
Yeah.
So I'm adding like D A's every time I do that.
Right.
And clearly now this is not in the language and you're done.
Yeah.
Yeah.
So the reason I wanted to remind about this example though is because it's not just that the whole thing had size greater than the pumping length, it's that specific portions were so long that the loop has to occur there. So like you could potentially make the the string in your language for the context-free one so long that certain things occur, that this whole v u v x, there's an upper bound on the size of u v x. So you could do like, I don't know, n 2n, and then c would be n or something, right? And now UVX is forced into the first part, right? So there's tricks. This is not the easiest one to use. I'm just going to tell you that right now.
Okay.
But
so
it illustrates a very important point, right? That you took advantage, and this is why I'm saying it's so comparable to the previous one. And there's going to be a bunch of cases, because unlike the original pumping lemma, you have two variables, right, that are going to get pumped in unison.
Okay.
Because think about it like this: if we're talking about this as a grammar again, let's think of this v as some string generated by a variable. Let's say a after some number of production rules.
Yeah.
Creates the string 0, 1, 1, 0, b1. Okay? Then if it can be produced by a, then it can be produced by a over here as well. Like if you're having some repetitive variable and it creates some substring here, then certainly it can also create it somewhere else where it appears.
Yeah.
Sort of thing. That's the high level of it. Yeah. That's basically the high level idea. Definitely recommend trying to force UVX to be something quite specific. And then you are going to have to break this into a bunch of cases though. That's just basically inevitable.
It seems like the easiest to do just A and B and C N.
That is actually an option, right? Because A, N, B, N, C, N satisfies the criteria.
Yeah, but it's a bit hard. I tried that one.
You did?
Yeah.
But the thing is, but then it just becomes the problem that he did in class.
Yep, but except like if you pump one of them, then C is always going to be equal to the other one. So it's always going to be in the language.
Okay. Well, let's think of. Why don't we think of some
true.
cases? So certainly.
But like A N B1 C1.
Let me think of the best way to give a hint without giving stuff away.
No, that doesn't make
Yeah.
sense. What if you split it in half? Because then no, that doesn't work.
You don't really know where the y is going to land. So forcing the u, v, and x to be somewhere is basically the best you can do in this respect, right?
Wait, is it UVX or is it VXY?
VXY.
That needs to be like less than n.
It seems like you don't want A and B to be of the same length for your
So-
express
Yeah.
reason.
I think that's the way to put it.
The one way I was thinking about like kind of have like B be like n plus 1. Like I was unsure like how to pump that part.
I mean, if you keep it like this though. So what was the case you said was giving you problems? And I'm gonna have to make that the last thing. What's the issue you were having with this one?
Like I mean I tried this one and I also asked on Piazza. Like it's really hard because like if wherever you pump there's always something that's equal to C. So it's hard to find something that's not.
There's always something equal to C, but C has to be equal to the minimum.
Yes.
Of
So
them.
which is gonna be n always. So one of them is always gonna be an n.
Okay,
So there's
but
always a
here's an
partition.
important thing about pumping. You get to pick I.
Yes.
What's important about this definition? And highly relevant to this question.
It can be 0. Oh, so then it's not the minimum anymore. Oh, amazing.
Does that make sense?
I never thought. I don't think I've all my pumping lemmas I use 0.
Yeah.
0 is highly useful in the pumping lemma
Mm.
in certain circumstances. This minimum thing makes it
Oh, wow.
relevant here.
What? I'm not.
Does that make sense?
Cool.
It'll still take you some time. I mean, there's just quite a few cases.
So like just to be sure, like you're gonna like it's either gonna be all in A's, it's gonna be A and B's, all B's, or B and C's, or C's. Like these are all the possible cases where you're.
There are a lot of cases.
But like these are all the possible ones, right?
Well, the
If you
y
pick
can
one.
be very far away from the v, right?
But you cannot like go beyond the limit because like the size is n, right?
The size of the whole thing is
Oh,
Let's go. Do you mind if we go back to pumping? I'm just.
Oh, the pumping lemma?
Yeah, pumping lemma. I'm pretty sure
Yeah.
that.
I can go over to this
this is-
definition though. Here's
Yeah,
the.
go to the. Yes, that's what I thought. There's no bound on the size of the whole string. But, oh right, VXY is bounded by n. Exactly. Yeah, yeah.
So
So, that
if
it
you-
can't cross over from A
That's
to
why you have
C.
like discrete set of places where it can.
Yeah, definitely.
Okay.
Sick.
Alright, that's.
Sorry, I wrote it actually wrong up here, because I had it's the middle part, the middle 3 that has to be less than n, which
Yeah.
is so I apologize for that.
No worries.
Makes much more sense too. I was like, that seems correct, but it's definitely not what I wrote.
Alright, cool.